We've been talking about eliminations, mostly pulling off protons and then having leaving groups leave. And most of what we've been talking about here has been pulling off protons and having leaving group leaves, but you can have other types of bonds here that can push out leaving groups. Beta silyl groups, especially siliconate anions, can push out leaving groups. We introduced this concept called a Peterson olefination. It's a great example where a siliconate carbon bond is nucleophilic enough to push out a neighboring leaving group. When we left off, we were talking about organometallic bonds, carbon-lithium bonds, carbon-magnesium bonds, Grignard reagents, alkylithium reagents. Those bonds are super nucleophilic. It shouldn't be any surprise to you that if you have a Grignard reagent anti to an alkoxy group, that you can push that group right out in an elimination reaction. So it's an elimination, even though you're not pulling off a proton, that bond there is nucleophilic. And I showed you this slick example of a trichloroethyl, trichloroethoxy carbonyl group where you could probably make a magnesium carbon bond, but they do this with zinc because it's milder. It's a mild way to deprotect these TEOC groups, the TROC groups, the trichloroethoxy carbonyl. I'm going to go to the last type of elimination that we're going to cover in this course, and it's completely non-obvious that you could use a carbon-carbon bond to push out a leaving group. I don't think it's obvious. Maybe we've seen things like that with migratory displacement reactions, but here's a version of an elimination reaction that uses a CC bond, and we're going to be up to our old tricks here. We're going to try to do something to weaken that CC bond and make it more nucleophilic. Weaker bonds are more nucleophilic. So we've got this same old trick. Look at this arrangement here. It looks kind of haphazard, but it's not haphazard at all. There's this OH group. You can see they're adding sodium hydride, and that's going to deprotonate that OH group first in order to make an alkoxide. And then there's a leaving group way over here. And that is not set up to reach across and have the O- do an SN2 type displacement reaction. That's not going to happen. What's going to happen right here? So you'll start off by deprotonating. Let me go ahead and draw out the sodium hydride. Sodium hydride is this solid, but we're going to depict sodium hydride with just a single bond here, and I'm going to use this nucleophilic basic, not nucleophilic at all, hydrido-sodium bond, and I'm going to make hydrogen gas. Also, I'll take the electrons away from sodium, and then I'll make H2 gas. That's irreversible, so that makes that a powerful base if the hydrogen gas leaves and it can't be reversible. And so now you have this alkoxide here, but you're not really set up to understand what's going to happen with this alkoxide unless we draw this CD ring of this steroid system using chairs. And the reason we're using chairs here is we want to emphasize anti-periplanar relationships by drawing chair-like conformations and drawing substituents on those chair-like conformations. So I've got these two rings, this 6,5 fused ring system here, and all we have to do is fill in the substituents. So I'm going to go ahead and draw this O- that's going down. See that O- we just created? That O- group is pointing downward. There we go. And that tosylate group is up. So there's an H atom over here on this carbon, and there's a tosylate leaving group. The tosylate is up. So over here I'm going to draw, it's a 5-membered ring, so it's not purely equatorial. We don't really need the H atom here, but I'm going to draw it anyways. It's kind of small. And there's that tosylate leaving group. And we have this great alignment here. This great alignment. Maybe I didn't draw it so great, but we have this great alignment here between this CC bond and that O-tosylate bond. That carbon-carbon bond that I highlighted in yellow is going to push out the tosylate leaving group. We're going to use the CC bond as a nucleophile. And why would that be a good nucleophile? Well, because we have this very naked O- here with nothing to do except donate into these CC bonds and weaken them. Right? All the CC bonds that are attached to this carbon here are being weakened by that O-. And so by weakening this CC bond, it allows that CC bond to move over and push out the tosylate leaving group. And we call this a Grobe fragmentation is the name for this process. When you weaken a CC bond and use it to push out usually a tosylate or a mesylate leaving group are the common versions of these. But you'll notice this reaction is stereospecific because there was a relationship here in this starting material. This methyl group up here was anti to that CH. And that relationship has to be preserved, because after the elimination, that methyl group right here, that methyl group right there, has to be on the opposite side of the double bond as the CH. From beginning to end, from the starting material to the product, that methyl group and that CH need to stay anti to each other, or else we've messed something up, or else the elimination wasn't concerted the way we depicted it. And we drew that CC bond pushing out the tosylate as a concerted process. Okay, let's just make sure we understand this requirement for anti-paraplanar relationships between the CC bond that we're weakening and the group that we're pushing out. So here's another substrate. Again, it looks kind of random, but it's not random. You have to very carefully choose what substituents. Now, you're probably not used to drawing fused ring systems, and you'll notice here that I've got two 6-membered rings fused together. When you have two cyclohexane rings fused together, we call that decalin. Sometimes you'll see people use decalin as a high boiling solvent. It's got a very high boiling point. But this particular decalin is not transfused. That would be very typical. This is a cis-fused decalin. So you see here at the ring junctures, both of those groups are pointing up, or if they were both pointing down, that's called a cis-decalin ring system. And you need to practice with drawing cis-decalins until you're good. Let me just write that out. That's a cis-decalin. Decalin is two 6-membered rings, 10-carbon system, decalin. Cis-decalin, and it's got a cis ring fusion. Now when you fuse those two rings, look how very careful I was about the way I drew this to make sure I preserve that relationship here. Right? This is one possible chair flip way to draw a cis-decalin. I could flip the two rings and draw it a different way, but this one just happens to be easier for us to see what's going on. Let me go ahead and draw these two substituents. You can see there's an H sticking up and an OH sticking up. Let me draw that H, the H sticking up first. That H is going to be at this back bridgehead. There it is. And that OH also has to be sticking up. That OH is over here on this carbon atom. But we already have a bond sticking downward, so the only place we can put that OH is equatorial. There it is, OH. I'm just going to write the O here because we're going to deprotonate that with the T-butoxide. T-butoxide is it's a pretty powerful base. It will generate a reasonable concentration, about an equal concentration of T-butoxide versus this alkoxide, so there's an equilibrium deprotonation that's occurring. I'm not going to draw the arrow pushing step for that deprotonation. You get the idea. T-butoxide pulls a proton off of that OH. And let's be very careful about the way we draw this tosylate, because you can see here that this tosylate group is going down, and that means that there was an H sticking up. And we want to make sure that we draw that tosylate in a way that clearly depicts the stereochemistry of that position. Now I'm going to draw over here two lines to represent an axial and an equatorial bond. Now that axial and equatorial bonds don't look like they're sticking straight up because the ring on the right-hand side is going sideways. So you shouldn't have that bond sticking straight up if your ring is sticking sideways. It should be sticking straight up relative to the ring. So I can't really rotate my screen here. Rotating my iPad wouldn't do anything. But if I could, this relative to this ring down below, the alkoxide is axial. That's an axial bond. And then this group over here is axial. And the tosylate is going down. So let me use I'll draw these two substituents in here. I can barely fit them in. That's the H. And over here is that tosylate, OTS. Great leaving group. Now this alkoxide is weakening. It's weakening the bonds. It's weakening all the bonds. The lone pairs on that tosylate are weakening all the bonds attached to that carbon. The lone pairs on that tosylate. Let me go ahead and draw that kind of the arrow pushing depiction. I'll go ahead and push downward. One of those three CC bonds is more likely to do something. Right, as we're pushing with those lone pairs, you can't stop the pushing. The bonds get a little bit longer, they're more nucleophilic, and that allows this bond over here that is perfectly anti-paraplanar to the tosylate leaving group to push out that tosylate leaving group. Again, this is another Grobe fragmentation. And there we go. Now, how do I draw that product? Boy, how do I draw that product without screwing something up? Here's what I'm going to do. I'm going to take a note I'm going to redraw. You can see what I'm trying to do here is I'm trying to redraw the exact same original system. And then I'm just going to erase this middle bond here, the CC bond that cleaves. And I'm left with a 10-membered ring if I erase that middle bond. Now I've done most of the work for you, but if you're good at drawing cis-decalin ring systems, then you'd be able to do that. And importantly, when I look at the two carbons that end up double bonded, that's back here. There's two H substituents on there, and I'm going to draw them, because if I don't draw them, I'm going to get messed up. I'm going to forget something, I'm going to screw something up. And you can see they are both on the same side of this bond where we're going to form the double bond. In the beginning, in some kind of a transition state, and then in the end, in this product. They should be syn to each other. So let me draw that new double bond. And over here, we're going to have this carbonyl group sticking off over here. Boy, that's not a good... Let me try to do a better job of drawing that carbonyl group. There's the carbonyl group. And so that double bond has to be cis. The two H's were cis to each other in the starting material. Those two CH's have to be cis to each other in the product. It's a stereospecific process. Eliminations are stereospecific. There's only so many ways to draw a 10-membered ring with a cis double bond in it, so I chose to draw it like this. I just wanted to make sure when I drew this that I didn't draw things in the wrong position. So relative to this, if I counted around, 1 from the carbon-carbon double bond, 2, 3, 4, 5, 6. I just want to make sure when I draw this out, boy, 1, 2, 3, 4, 5. Oh man, unfortunately I flipped the ring. So whatever, that was a bad maneuver. 1, 2, 3, 4, 5, 6. The carbonyl is six atoms away from the first carbon of the CC double bond. I wish I hadn't flipped the ring around because it just makes it confusing. You just want to draw a 10-membered ring product where there's a carbonyl 6 atoms away from the double bond, and it has to be a cis double bond, a Z configuration. All right, so eliminations. So we talked about pulling off protons and having leaving groups leave in every possible order. Right? We had the leaving group leave to make a carbocation, then pulled a proton off. That's an E1 elimination. We pulled a proton off to make stable carbanions when there was a stabilizing group. That's an E1CB. And then you push out the leaving group. And then finally we talked about E2, concerted E2 eliminations. Boy, such a strong requirement for antiparaplanar relationships in E2. And for those types of E2 eliminations, you can have carbon-metal bonds pushing it out, weakened CC bonds pushing out the leaving group. It all kind of fits into the same continuum. All right, so that's it for eliminations. Now let's move on to a hugely different topic now. So we've been talking about eliminations, which is a way to add to sigma star and push out leaving groups. And we've talked about addition to pi star, like addition to carbonyls. We've talked about addition of nucleophiles to iminium ions. We've mentioned addition to carbonyls that are protonated or maybe have a Lewis acid attached to them. But now we're going to talk about double bonds that are acting as nucleophiles and attacking other things. Right? If you knew nothing more, you'd say, well, a double bond's not going to be as reactive as a lone pair. That's true. But if we're very careful to exclude lone pairs from our system, or if they can only react reversibly, now we're set up to start talking about things like CC double bonds acting as nucleophiles. And in this case, it's going to be the pi-like orbital, right? I'm drawing out a pi-like orbital here, pi CC, adding to some electrophile. And we're first, in this topic, going to talk about addition to heteroatom electrophiles, like Br2, Cl2, epoxidation, making carbon-oxygen, carbon-halogen, carbon-boron bonds. And then we'll switch over and talk about the very interesting and related process of adding CC double bonds to carbenium ions. But that'll be a way for us to frame this conversation. Okay, so let's go ahead and talk about how to depict arrow pushing using simple CC or CN or CO double bonds. So if you take an imine and you react that with some sort of a carbenium ion or maybe even a proton, what part of the molecule should we use for the arrow pushing? Right? I could use the lone pairs like this and attack the electrophile. Oxygen lone pairs, I could attack the electrophile. Or I could use a pi bond. Right? If I have a CC pi bond, there's no lone pairs on that, but it's natural to use the pi bond. But what about this? If I have an imine, can I use that lone pair to attack the carbonium ion? Why not? I mean, it's going to give a resonance structure of using the lone pair of the same thing I would get if I used the lone pair. Why not use the CO pi bond to attack the carbonium ion, or the proton, or some other electrophile, or boron, or the Lewis acid? Is there anything wrong with using that pi bond? Yeah, there's something big time wrong. If you're just talking about simple imines and simple ketones and aldehydes, just remember, pi-like orbitals are lower in energy than lone pairs. If you've got a lone pair, use the lone pair on that atom. If it's just a simple imine or a simple carbonyl, like an aldehyde or a ketone, use the lone pair. It doesn't make sense to use the pi bond. We already know that pi bonds are lower in energy than the lone pairs, if all things are equal. Okay, but let me throw a caveat in there, and this is a huge caveat. Quite often, we have donor groups right next door, like nitrogen or oxygen, the nitrogen of an amide, oxygen of an ester. And here we have a choice for how to depict this. So if I have an amide and I want to draw out acid-catalyzed hydrolysis, my step one is going to be, no way I'm getting an oxygen water molecule to attack that carbonyl unless I protonate that first. So I'll add my electrophile to the lone pair, and that makes total sense to me. It explains why the carbonyl group should be reactive towards a lame electrophile, lame nucleophile like water. Here we go. Here's the protonated carbonyl. You still have to heat it, but at least at high temperature you can get water to add to that. There we go. Now there's another way you could depict this. You could use the pi bond to attack that proton, like this. And I wouldn't complain about that at all, as long as you start with the nitrogen lone pair. You know, when that nitrogen lone pair donates into the carbonyl, you create two new orbitals, and one of them is a high-energy pi-like orbital. It actually makes sense to have a pi-like orbital that's spread out over those three atoms, N, C, and O, that is very nucleophilic and basic. And when you generate the structure for this, it looks like this. If you follow my arrow pushing, and these are resonance structures of each other. So I've told you before in this class, well, if your arrow pushing generates a resonance structure of my arrow pushing, I'll count those as the same thing. It's good enough. So in particular, when you have esters and amides, totally okay and appropriate even to start with the lone pair down here. That actually does a good job of representing the frontier molecular orbital, which is very pi-like. But if you want to protonate the lone pairs every single time, whether it's a ketone, aldehyde, amide, ester, that's good too. That's good for this class. So both of these are okay. I'll just write okay here because that's, and again, they both lead to a resonance structure they both lead to this different resonance depiction of the same thing. So both of these depictions are okay. Okay, so let's go ahead and talk about pi bonds as nucleophiles. We're generally not going to be using carbonyls and imine pi bonds to attack things. It's not really typical. We're going to be using CC double bonds because most organic chemists care about making bonds to carbon. That's usually the main driving force when you make medicines, pharmaceuticals, bioactive molecules, functional molecules that do things, polymers. We're usually making bonds to carbon. Okay, let's go ahead and talk about trajectories here, or maybe it's not so much the trajectories, but we need to think about orbital phasing here, and I want to remind you of a simple idea. I want to remind you that when you add nucleophiles to double bonds, nucleophiles, let's just step back to a previous lecture, we said that when you add nucleophiles to double bonds, that the nucleophiles come in at some sort of an angle. Right? If you've got some nucleophile with its unshaded orbital here and you want it to interact productively to make a bond, you want to avoid interactions with the gray shaded orbitals of pi star. And the only way you can avoid interacting with the gray shaded part of pi star is to come in from an angle. Right? If you have orbitals with opposite phasing interacting, you break bonds. That's an energetically unfavorable process. And when we do this, we're going to end up with some sort of a system that looks like this, and after you add, the lone pair that you generate ends up anti in an orbital that is anti to the original nucleophile. There's this anti-relationship, and it is perfectly set up stereoelectronically to push the nucleophile back out if the nucleophile is something like water or chloride. So notice that anti-relationship. Nucleophile comes up on the top of the double bond, the lone pair appears on the bottom of the double bond. That's just a natural consequence of the phasing. Right? You add electron density to here, it appears down here at the bottom in that orbital. And vice versa. Right, if you're pushing a leaving group back out, you'd see that same deal. So it should not surprise you, this whole idea. Let's just suppose that our nucleophile were attached. Suppose this nucleophile over here were attached, like a carbon-silicon bond, or a carbon-tin bond, or a carbon-lithium bond, or a carbon-magnesium bond. Any kind of nucleophilic bond, if you had that right next door to pi star, you should expect this same sort of enhancement of reactivity on the opposite side. If this orbital, right, if this bond right here is really donating into pi star, it should make the bottom side here. It should make the bottom side of that, let me take that last dot out. It should make the bottom side more reactive. It's almost like the CC double bond is going to be reactive here on the bottom. Just like if you add another nucleophile to a CC bond intermolecularly, right, you generate a lone pair on the bottom. So if you have a carbon-silicon, carbon-tin on top, the double bond becomes reactive on the bottom. Right? This is just like when we add lone pair nucleophiles into carbonyl groups. Let's take a look at the consequence of that. Most of our CC bond-forming reactions are in the next topic, but let's go ahead and take an example of that. Here's an allylsilane down here, where you can see somebody went through a lot of trouble to put the allylsilane on top here, so that we could follow what's going on. And we're putting in an electrophile that's good for SN2 reactions. You can do SN2 ring opening of an epoxide that is coordinated to a Lewis acid. So if you take an epoxide, they're not so easy to open up, but when you coordinate epoxides to Lewis acids like boron, titanium, stannate, stannic SnCl4 Lewis acids, that O plus is not very happy. And so it should make sense to you that we can just open that up. And let me go ahead and open that up over here. Let's do this. I'm going to use this nucleophilic bond there. See that bond? And then I'm going to give the electrons to this oxonium ion. And that stupid charge is in the way. I'll just go around it. There we go. So we're going to make a CC bond. And really the question is, what face of that double bond do we tack on? Do we make a new CC bond on the top face where the silicon is? Or do we make a new CC bond on the bottom face where the silicon is not? And that's an easy, based on what I just told you up above, right, what we're going to do here is we're going to make this sweet beta-silocarbenium ion. Look at that. Just can't get enough of that. There we go. And our electrophile needs to be on the bottom face. This is not a steric. The sterics has nothing to do with this. This is all driven by stereoelectronics. So the titanium is still a titanate, negatively charged titanium. And now we're going to have some arrow pushing where the chloride, I'm not going to draw all of this out. We'll do more of this later, where a chloride pops out of the Ti minus, and then it comes in and nails the silicon, and you break the silicon carbon bond. But in the end, you'll end up generating a product where the new carbon-carbon bond is on the opposite face of where that silicon was. And eventually you'd end up transferring that oxygen to the silicon, but I'll draw out this intermediate there. Okay, so I'm not going to draw all the steps there. Chloride comes off, hits the silicon, and then we should be starting to see more and more of those types of silicon beta-silocarbocation reactions. Okay, so you got your nucleophilic bond on the top, and so the pi bond of an allylsilane or an allylstannane or an allyllithium or an allyl-Grignard reagent or an allyl-boronate should be nucleophilic on the opposite side of where that bond was. Okay, I want to come back to another consequence of this orbital picture that we have. So we mentioned that because of the phasing of a pi star-like orbital, the nucleophile wants to come in so it minimizes destructive interactions with this gray shaded part of pi star. You come in from an angle, very specific angle, 109 degrees, just like the angle in tetrahedral methane. It's called the Bürgi-Dunitz angle. We're not going to go a lot into stereoselectivity in this course. That's a whole nother course that would be awesome if we had time. So nucleophile attacks from a 109-degree angle, that's what happens when nucleophiles add to double bonds. But what about this topic where we're adding electrophiles? What about this topic where the CC double bond is the nucleophile and we're attacking some other thing, like a proton, like a carbocation, like Br2, like hydroboration oxidation? Now it's a different orbital. If we draw these orbitals out, if I sketch these orbitals here, let me go ahead and draw out pi star. Pi star looks like this. This is the kind of structure of pi star. And when you come in with your nucleophile, you want to avoid interactions when you add to pi star. That makes sense. But now, if I draw pi, pi looks like this. It's like this, I don't know what you call that, a hamburger bun or hot dog bun that's been split. And now, when your electrophile comes in, you want to come in dead center from that double bond. I mean, if the alkene is symmetrically substituted, now we don't have to worry about bad interactions as long as we stay on one face of the alkene, top or bottom, right? We want to come right in from the middle. And these angles are going to be close. It's not exactly 60 degrees, but I don't know, it's somewhere between 60 degrees to 90 degrees, depending on what the what this angle is here. It's not 109, it's an acute angle. You come in from the middle of the pi bond. That should make sense. So our trajectories are different. Let's take a look at some consequences of that. Again, we're not going into big detail here with stereoselectivity, but all of these ideas, you don't need to know anything other than the orbital shapes to predict stereoselectivity. Let me take an example down below here. And let's just imagine that we're adding some sort of a nucleophile to this carbonyl group on a cyclohexane. And just to make sure that we've added some steric hindrance here, we've got maybe 2 methyl groups or 2 ethyl groups or a spiro ring fusion, something to kind of get in the way of a nucleophile. As long as you have an R group axial here, it makes it very, very uncomfortable to come in from one face versus the other. It becomes very uncomfortable. If I want to come in from that 109-degree angle relative to the CO, that would be down here. My nucleophile has to be sitting right there on that R carbon bond. There is no way a nucleophile is going to fit down there. If I want to come in from a 109-degree angle on the bottom, look at that. So free and easy there. Boy, that's easy. Now, if you look at the relative stereoselectivity for addition of alkylithiums, of Grignard reagents to these types of axially substituted cyclohexanones, the trajectories for attack, when you look at the product ratios, it's 0 to 100. You add from the bottom face. There's no nucleophile that's going to sit right where that R carbon bond is and attack from a 109-degree angle. Just too hard. But now let's take the opposite case. Let's suppose we take a CC double bond and use it as a nucleophile. If we look over here, now we're using the CC double bond as a nucleophile. And the electrophiles will attack from the middle of the double bond, and that's much more relaxed. So coming from this kind of trajectory, either from the top or from the bottom, we don't come in from this horrible angle here. We come in kind of from the top or the bottom. And there's still a slight preference, but it's not a huge preference anymore. So now with an electrophile that can add top or bottom, that's supposed to be an E. That's really poorly drawn. Let me redraw that E. Or E plus adding from the bottom face, right? Turns out that you get about a 60-40. Not 100 to 0, 60-40. So now there's a little bit of hindrance here, but nothing like addition to that carbonyl. So there's still a slight thing here. Whereas here, this is just like, ow, ouch, man, no way. So alkenes are nucleophiles. We're adding to, now if we're using alkenes as nucleophiles, it's pi, not pi star. It has profound implications for stereoselectivity. And that's a fun class to teach and take, is stereoselective or organic chemistry, where you think about how to control stereogenic centers, dash, wedge, stuff like that. Okay, so let's talk about some simple additions of electrophiles that you should have seen before. You should already know these types of reactions. Addition of Br2 to double bonds, you should know that. Addition of Cl2 to double bonds, you should know that. And if you don't know that, go back and work those practice problems that I put in our Canvas files. There's a lot of of practice doing exactly these kinds of reaction mechanisms. So let's go ahead and take a look at the addition of Br2. How do we push arrows for that? Remember, the basics of this reaction is that you're using a pi bond to attack and displace a Br minus leaving group. Look at that. I didn't do a good job. That Br bond is long. It is weak. Anytime you have two heteroatoms bound to each other, OO, ON, O chlorine, OBr, that is a weak bond. Even if it's two second row atoms, OO, that's weak. That is so weak. It's going to break. So easy to break this. Now, we're not going to generate a carbocation when we add to this. If I just drew the arrow pushing the way I've drawn it here, I would be forced to draw a carbocation at one of those two carbons of the CC double bond. That's not the way these reactions work. Because the closer that bromine gets, the closer the Br2 gets to this double bond, the closer these bromine lone pairs get. And as you generate a carbocation, the lone pairs will come back in and add in. Now I can add in to either one of these two carbons. I could add the lone pair into this carbon. I could add the lone pair to that carbon. The fact is it's adding into both of them simultaneously. And so we're going to get this cyclic bromonium ion intermediate. It's arbitrary whether I attack this carbon. That's not a, let me avoid. It's arbitrary whether I attack the left carbon or the right carbon. I'll attack the left carbon with that lone pair. Doesn't matter. The point is that I'm going to generate this cyclic bromonium ion. There's no carbocation usually, or well, in this case, for simple alkenes, when you add Br2, Cl2, N-chlorosuccinimide, which has a weak chlorine-nitrogen bond. Let me go ahead and draw out this. I'll try to draw this as trying to figure out how to draw this. Here's my cyclic bromonium ion. There we go. And if the two R groups started out anti to each other, they better stay anti in the next intermediate. They have to be on opposite faces of this cyclic bromonium ring. So we end up with this cyclic bromonium ion, and then the Br minus will float all over the place until it arrives here on the bottom face, and now that Br minus can open up that ring. And we're going to get, the result will be anti-substitution. Doesn't matter in this case which of these two carbons I open up, left or right, it's arbitrary. If I open up on this side, I'll get one enantiomer. If I open up on this side, I'll get the other enantiomer. You will get a mixture of two enantiomers in this reaction. There's no way to prevent that because, at least for this simple case where R is achiral, there's nothing to control which side. According to my arrow pushing, the bottom Br, my arrow pushing says that the bottom Br must have added over here on the left side. So let me make sure that I follow through with that. So let me open here. There we go. And I'll pop open this carbon-bromine bond. So the result is anti-addition. It's not going to be obvious that it's anti-addition. If you had a cyclic alkene like cyclohexene, cyclopentene, it would be totally obvious that the addition occurs anti to each other. Now, you want more nucleophilic double bonds. And the substitution on the double bond has a huge impact on the rate at which CC double bonds act as nucleophiles. I'll go ahead and give you some numbers here that are taken from actual measurements for rates of reaction with Br2. One of the least reactive alkene double bonds, the least reactive alkene double bond that I can envision just off the top of my head, maybe fluorine CF3s could reduce it, is just plain ethylene. I'm going to assign that a relative rate of 1. I mean, there is nothing on that CC double bond that can donate into it and make it more reactive. I feel like, gee, I want to put a carbon-silicon bond, allylic to that, or a lone pair, O minus. Those would really soup it up. But the worst case, maybe not the worst case, but even an alkyl CH, if I have an alkyl group with CH bonds, those CHs can donate into the alkene and soup it up. So if you have alkyl groups on any double bond, they will soup up the rate of the nucleophilicity of that double bond. So here's just a simple terminal olefin at the end of an alkene chain, and this is 100 times more reactive than just an ethylene molecule. And that's all because of these CHs here, the CH bonds that are donating into the alkene and making the alkene more reactive. Now you get a slight increase in reactivity if you have methyl groups on both sides. Now that's 1750, like 2000. It's about an order of magnitude more. Who cares about the factor of 2? We're just interested in the factor of 10. About 10 times more reactive when we have two alkyl groups on that. And if I put the two alkyl groups on the same carbon atom, it's a pretty sizable increase. It's almost like, gee, if you added an electrophile, it makes you think, gee, if I added an electrophile right here, straight up, I would end up with a really stable carbocation over there. Right? If you would like to think of product stability, that's not really the right way. But both of these CHs, when they're donating, both of these groups have CHs, the methyl groups have CHs on them, and both of those CHs are donating into this pi system to make this end carbon more nucleophilic. So in the transition state, you're going to have more. When you finally reach that hump, that energy hump in the transition state, you'll have more bond formation here than here. But the Br2 will add to both carbon atoms in your arrow pushing step. Okay, if you put tri-substituted olefins here, right, that's about as hot as you can make it. Look how much more reactive this is with a tri-substituted olefin. 138, whoops, let me do it in red. 138,000 times more reactive than ethylene. Wow. What if you could do your homework 138,000 times faster? Right? That makes a difference. Right? If you had to go into the lab and run a reaction for your PhD and it took 138,000 days versus 1 day, right? You want to do things that are 138,000 times faster. So if you ever see somebody trying to add electrophiles to simple alkenes, you need to be thinking, boy, that's not so fast. Right? Try substituted alkenes. Boy, that is fast. And when you look at how nature assembles complex ring systems using electrophilic addition to alkenes, it uses tri-substituted alkenes. Nature's no dummy. Nature knows exactly how to make things work well and work fast. Now, let me talk about this cyclic bromonium ion thing. When you add Br2 or Cl2 or bleach, that would be HO attached to chlorine. Right? You need to draw this out as a concerted process, right? Break the weak bond there. There you go. But there's a lone pair on that bromine that's going to come back in and attack. And I can make that lone pair attack either carbon of the alkene. Doesn't matter. You'll get the same product. Your arrow pushing will give you the same product. And so in this case, our intermediate, our reactive intermediate that we generate would be this cyclic bromonium ion, just like we did up above. But what happens if I change from an ethyl group to a methoxy group? And this is now different. And I told you, like 95% of our arrow pushing we do in this class is going to start with lone pairs. It's kind of hard to find molecules that have no lone pairs on them. And if I draw the lone pair over here in this oxygen atom, right, that's going to make that alkene more reactive. This is called it's not an alkene, it's an enol ether. It's a different functional group. And those lone pairs are souping up the reactivity of this CC. Not randomly, it's souping up the reactivity of this end carbon. Let's go ahead and draw that out with arrow pushing. And so when you draw out the arrow pushing for an enol ether or an enol, this is the way to do it. You just break the bond, and that's it. You don't make a cyclic three-membered ring onium ion. If you drew that out, I wouldn't say you're wrong. I mean, there is a simultaneous interaction. When this Br2 lands on top of this alkene, it is actually, there is some interaction with both of these carbon atoms in the HOMO. But when you do this for arrow pushing, the better way to draw this out is to simply draw this as generating just a simple oxonium ion intermediate. You're just going to create extra steps, and it's not really that accurate to draw the cyclic bromonium ion. So again, if this is an enol ether or an enol or an enamine, and you're adding Br2 or Cl2 or chlorohydroxy, that's bleach, or N-chlorosuccinimide, you don't need to draw that three-membered ring intermediate. I'll just write not. This is the best way to depict this if you have, souped up, amped up pi systems that are made nucleophilic. Okay, when you go back and you look at whatever text, I don't know what textbook you used for sophomore organic chemistry, they talk about addition of Br2 across double bonds, they talk about addition of Cl2 across double bonds. They do not talk about addition of I2 across double bonds. Right? So let's talk about that. What's wrong with this? I mean, if you think about the chemical reactivity of I, an I bond is longer, it's weaker, ought to be more electrophilic. I mean, You'd think that it would react faster and better. So why is it that we don't ever see addition of I2 across double bonds? That would be great because carbon-iodine bonds are more reactive. Seems like you'd want to add I2. There is no problem whatsoever with the rate at which the II adds to this system. That's not the problem, right? This is perfectly fine. And then I'll come back in with these lone pairs and add that in. There's nothing wrong with this, with the rate of this reaction. There's nothing wrong with this intermediate, right? I could have an iodonium intermediate just like I could have a bromonium ion or a chloronium ion. And then this I minus could come back in and open this up. Let me draw these going up here. Let me circle that charge so it's clear that's an iodonium. There's nothing wrong with this arrow pushing. The rate of these reactions is not the problem. The problem is the stability of the product. The problem is that the equilibrium constant, because carbon-iodine bonds are so weak. Your product ends with 2 carbon-iodine bonds, carbon-carbon double bonds are not great. They're not as stable as carbon-carbon single bonds. But if we just traded a carbon-carbon double bond for 2 lame, I was going to say lame-ass, but maybe that's the best term, 2 lame-ass carbon-iodine bonds. The starting materials were more stable than the product. And that's not true for Br2, Cl2. Those are thermodynamically favored. It's just that the equilibrium constant favors the starting materials. So these would be in rapid equilibrium in this case. So I'm not going to go into what would you have to do to make this a facile process. There's some systems where you can do this if you change the conformation. All right, and let me just be clear, right? I'm telling you with these reversible arrows that this can go back. This is an example of neighboring group participation, kind of like sulfur lone pairs can push out leaving groups, nitrogen lone pairs can push out leaving groups. Those I lone pairs can push out the neighboring iodide to give you back the cyclic iodonium ion. Now, if you're adding a different nucleophile in here that makes a stable bond, you can use these cyclic iodonium intermediate. So here's an example over here. I think on one of our very first problem sets we had a reaction like this where we were doing an iodolactonization in this case. So here they're using iodine and they've got these nucleophilic lone pairs here on oxygen and those will cyclize around. Let me go ahead and draw out the intermediate we would get if we added I2 to this system. Boy, I better hurry. I'm running out of time. You know what, I'm not going to have time to, it's not a long mechanism. There's only one intermediate to draw, but I'm going to go ahead and hold off right there. So when we come back on Wednesday, we'll finish up this mechanism and talk about how you can make a cyclic iodonium ion, but then trap it by forming an oxygen-carbon bond instead of a weak carbon-iodine bond. And that's a good way to take advantage. And then you have this lovely carbon-iodine bond on your product that you can do all kinds of things with. Okay, work problems, those mechanisms in those that I put in our Canvas files on that page. It's just got lots and lots of reactions. And there's a whole chapter in there on alkenes acting as nucleophiles and attacking things. That's perfect for this section.